Alright, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we are going to be talking about Newton's universal gravitation. As more precise, it's probably called Newton's Law of Universal Gravitation. Alright, so this is something that Newton studied in his lifetime and came to the conclusion that two bodies, no matter how massive or how small they are, exert a force of gravity on each other. So if you have mass, you have the ability to exert gravity on other objects with mass around you. I think he studied this mostly with celestial bodies. It wasn't shown until, I'm trying to remember who was it. I want to say Hooke, but I'm not sure. But anyways, another scientist after Newton, she proved this using an apparatus on Earth to show that no matter how massive your body was, you could attract other objects to yourself. Okay. Anyways, in Newton's study, he came with the following formula for universal gravitation. Okay. So this is force of gravity. So that's Fg. That's force of gravity. Is equivalent to big G times big M times little m divided by r squared. Okay. Now, big G is what's known as the universal gravitational constant, and it has the following units, or the following value. So 6.67 times 10 negative 11 with units of Newton meters squared per kilogram squared. R squared is the separation distance between the masses. And big M and little m are the mass of the objects. Big M being the mass of the heavier object, and little m, so big M, mass of the heavier object, and little m being the mass of the smaller object. Okay, you could easily call them M1, M2. I think some textbooks will describe them as M1, M2. Other textbooks describe it as big M and little m. Okay. Now, there are some really neat aspects to this particular formula. So here's the formula again, and using mathematical proportions, it shows that the force of gravity is directly proportional to both masses, because they're here in the numerator here. So the force of gravity is directly proportional to the mass of the objects, and it's inversely proportional to the square of their separation distance. So in a way, it means then that in order for the force of gravity to increase, you have to do two things, I guess three things. You can either increase the mass of the large object, you could increase the mass of the small object, or you can decrease their separation distance. By doing any of those, it'll cause the force of gravity to increase. The opposite is also true. So if you want to decrease the force of gravity, you can decrease the masses or increase their separation distance. Okay. And that's really interesting. So the force of gravity gets stronger as you get closer to an object, and it gets weaker as you get further from an object. Okay? All right. Oh, and then this G is constant, so this is a constant value. In your textbooks, there should be on the back cover of your textbook a table of constants. You should be able to find big G in there. Okay, so that's Newton's law of universal gravitation, is that the force of gravity actually depends on the mass of each object and how far they are from each other. How does this relate to the force of gravity equation we learned in Physics 11? We'll talk about that in a moment. But first, let's go through an example of working with this formula. So in an example, let's calculate the force of gravity between a 25 kilogram box and a 35 kilogram box, and we separate them by 2.5 meters. Okay, so here is kind of the situation we're looking at. All right, so our formula, I'll write it out here. Force of gravity is equal to G big M little m. Well, again, you can use M1, M2 over R squared. Sometimes some textbooks will go little r squared. Big R is kind of, you'll see why I use big R in the next example. All right, so we'll calculate this out. So G is 6.67 times 10 to the negative 11. It has units of Newton meters squared per kilogram squared. You'll see in a moment why the constant has the units of this value. It seems kind of arbitrary, but there's a reason for that. The big M, so the larger mass is 35 kilograms. The smaller mass is 25 kilograms, and they're being separated by a distance of 2.5 meters. There we go. Alright, so let's pull up a calculator and let's calculate this value out. So 6.67 to the negative 11, oops, 6.67 E, there we go, negative 11 times 35 times 25 divided by 2.5 gives us a force of gravity of something really, really tiny. So this is 2.33 or 2.3 if I'm using proper significant figures times 10, and it looks like it is to the negative 1, 2, 3, 4, 5, 6, 7, 8 to the negative 8. Makes sense. And then the reason for these units is if I take my units and start canceling things out, my kilograms squared will cancel out those kilograms. Oh, I messed up. This should be squared. So that number is actually a little bigger. But that this meter squared will cancel out that meter. So my final unit will be in newtons. I have to carry out one more division. Divided by 2.5 again. There we go. So now it's 9.3 times 10 to the negative, looks like 1, 2, 3, 4, 5, 6, 7, 8, 9 to the negative 9. That makes more sense. There you go. So if these two objects, between these two objects, there's a force of gravity of 9.3 times 10 to the negative 9 newtons. So what it basically means is that this object, there's a force pulling it this way of 9.3 times 10 to the negative 9 newtons. And because of Newton's third law, there is a force pulling this object this way of the same amount, 9.3 times 10 to the negative 9 newtons. Right. That's really neat to think about that. No matter where you are in the world, if there's an object of some mass, it's going to be pulling on you. And similarly, you would be also pulling on some object around you because you have mass. Okay. Now, what's up with the big R? Okay, why big R? So the big R is because if you think back to when we first started talking about gravity, we talked about G. And I would sometimes mention that G was known as gravitational field strength, and sometimes G would have units of 9.8 newtons per kilogram, like some parts of your textbook. This is the unit that G had. More often though, we would use G as the acceleration due to gravity, which is 9.8 meters per second squared. Both units are the same, by the way. If you do the dimensional analysis, if you take the Newton per kilogram and analyze it based on what the Newton is, then you'll get the same unit as this. Okay, now why is it sometimes called gravitational field strength? Well, if you look at the equation for force of gravity when we first introduced it in Physics 11, you got this. And by all rights, this is perfectly fine for Earth-based problems. Fine for Earth-based problems. But as I mentioned, gravity, a lot of this universal gravitation was studied using celestial bodies, or bodies in space, and they're much, much bigger. Compare this to the law of universal gravitation that Newton developed, and you got this equation, where the force of gravity is big G times big M divided by big R squared. Okay. If you look at the two equations carefully, they have one thing in common. They both have a little m in there, so that's a mass of an object. And using mathematical reasoning, that would mean that this G is mathematically equivalent to this portion of the universal gravitational equation. So it means then that G, the gravitational field strength, so this value here, otherwise known as the acceleration due to gravity, is actually the product, or it's actually the value of this. Okay. Now, big M, in this context, big M ends up being the mass of the planet, in our case, Earth, and big R ends up being the radius of the planet. Okay. Sometimes you can think of the radius of the planet as kind of like how far you are from the center of the planet, but we kind of stick with the radius of the planet because for the most part we don't ever leave the planet's surface. We don't leave, we don't get above the planet's surface to a degree that the G changes too much. For the most part, right? And to show how this works, let's take our next example is we'll calculate G at the Earth's surface. Okay. And we'll use, because of the way that the Earth is arranged, we'll use like kind of like the average Earth's radius. Because obviously the Earth's radius will change if you're, say, like on top of a mountain or if you're in a very deep valley. Okay, but we're going to take the average of the Earth's radius for this, which is this value here. And then this is the Earth's approximate mass. All right, so let's write down. So we only want to calculate G. So we only need to calculate this portion here. Over R squared, and that's G. Now the big G doesn't change. That is still going to be 6.67 times 10 negative 11. Let's put in our units: Newton meters squared per kilogram squared. We're going to multiply this by the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. And then we're going to divide this by the Earth's radius squared, so 6.38 times 10 to the 6 meters squared. So the meters squared will cancel out the meters. The kilograms here will cancel out one of the kilograms. So my gravitational field strength should have a value of newtons per kilogram. All right, let's do the calculation. So 6.67 to the negative 11 times 5.98 to the 24. We'll divide this by 6.38 to the 6, and then we'll divide it again by 6.38 to the 6, and this gives us a value of, look at that, very close to two significant figures. I can go three significant figures, which is basically the same, 9.80 newtons per kilogram. Obviously this will change, so if the Earth suddenly got more massive or if the Earth suddenly got less massive, then the G will change. If the Earth radius changed, G would also change. Okay, and this is kind of how we get the different gravity values for different parts of the solar system. So if we want to calculate the gravity of the moon, we would use the same formula, this formula here, but then this would change based on the planet. Depends on planet or moon or whatever. I mean, you could calculate your own gravitational field strength if you assume yourself to be a sphere. Take an average radius of whatever you imagine yourself to be like. If you're a sphere, then use your mass and you can calculate your own gravitational field strength. Okay. Another example, this one is here. Suppose you have two people and they're attracted to each other strictly by gravity. How long will it take gravity to pull them together if one person is stationary on a bench while the other is 2 meters away? So here we're gonna do a couple of things because it's asking us how long will it take? How long will it take? All right, so let's do our first thing. Let's calculate the force of gravity. So we're going to assume that the person on the bench is stationary. This makes the problem a little simpler. Not entirely accurate though, because if both people were not stationary, then they would both be moving towards each other. So the actual time might be slightly smaller if they were not stationary. But one of them we'll assume this person is stationary. So stationary. Being on the bench, we'll say that person doesn't move. We can calculate the force of gravity in much the same way as example 1. So F equals gmm over r squared. So let's do that first. I will skip writing the units because we have shown you how they cancel out. One person weighs 55 kilograms, one person weighs 50 kilograms, and they are separated by a distance of 2 meters. All right, let's calculate this out. 6.67 times 10 to the 11 times 55 divided by 4. All right, so here's the total force. Looks like 5.0 times 10 to the negative. It looks like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 to the negative 8 newtons. All right, so that's the amount of gravitational force that they are being attracted to each other with. Now, to figure out how long it'll take, we need to figure out how fast this person is accelerating this way. If there are no other forces acting on this person, then this will be my net force. And using Newton's second law, we can show that net force is equal to mass times acceleration. So if I have a net force of 5.0 times 10 to the 8 newtons, or sorry, negative 8 newtons, and my object, in this case the person in the backpack, has a mass of 55 kilograms, we can calculate their acceleration. It's going to be a ridiculously small number. So their acceleration, meters per second squared. Okay, so we'll take that number, divide by 55, is really tiny, 9.17, 9.2 times 10. And it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, wait, 10 to negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, to negative 10. To the negative 10. There we go. So that's how fast the person is accelerating. Very small acceleration. And then the time it takes, we'll go back to one of our kinematics formulas. So we're looking for time. If the person with the backpack starts with no initial velocity and all we have is a distance, 2 meters. Is it 2 meters? Yeah, 2 meters. And we have an acceleration of 9.2 times 10 to the negative 10. I think we will end up using this formula. D equals VIT plus 1/2 AT squared. Doing a little bit of rearranging, we can show, well, this is 0. We can show that distance, so 2 times distance over acceleration is equal to t squared. So square root that, 2d over a is equal to t. All right, so let's calculate t. So 2 times distance, so that'll be 4 over my acceleration of 9.2 times 10 to the negative 10. That'll be t. All right, let's move this over so I can see what I have. So 4 divided by 9.2 to the negative 10 gives me a value of, that is really large. So this is 4.3 times 10 to the, oh, I'm going to square root that, to the, oh, that's huge, 1, 2, 3, 4, 5, 6, 7, 8 to the 9, equals t. And then if I square root that, I get an answer of time will be 66,000, approximately 66,000 seconds, give or take. Yeah, 66,000 seconds, give or take. We're like 6.6 times 10 to the 4. There we go. So they're 2 meters apart with only gravity pulling them together. It'll take that many seconds to pull them apart. Now, that's actually not a very good time unit in this case. So let's divide it by 3,600 seconds in an hour. So seconds per hour. So approximately 18 hours. 18 hours. quite a lot of time to, if all you're relying on is gravity to attract you to somebody who's 2 meters away. Now imagine if they were even further than that, it would be quite an ordeal. So lesson here, you can't really rely on gravity to just pull you together. It's gotta be a little bit more than that. All right. Okay, so there you go. So that's Newton's law of universal gravitation. Basically, two objects will attract to each other as long as each of them have mass. If an object doesn't have mass, so it's a really fun thing to think about. If an object doesn't have mass, does it actually get attracted to other things? Right? Because according to Newton's law, in order to have a force of gravity acting on you, you need some amount of mass. Interestingly enough, what we do know is that, consider like light. Light has technically no mass, but it is affected by gravity. If the object is large enough. That brings a whole new other thing. If you remember from physics 11, we had mass energy equivalence. So light, being a form of energy, does actually have some equivalent mass, which is kind of neat. Anyways, your assignment, if you have your textbook, is as follows. This will just cover more universal gravitation stuff. And here's kind of a neat bonus. At what distance in space do you have to be so that the force of gravity from the Earth is equal to the force of gravity from the Moon? I'll give you a hint to this one. We'll only calculate if you are on a straight line between them. So at some point between the Earth and the Moon, so here's the Earth, here's the Moon, there's a point here, somewhere in between them, where the force of the gravity due to the Earth is equivalent to the force of gravity due to the Moon. Okay, it's a really interesting point in space, because it basically means that if you place an object right here, it won't get any closer to the Earth and it won't get any closer to the Moon, because both objects are pulling on it with equal force. Okay. Fun fact: this is called a Lagrange point, and they are really interesting locations in the solar system, because those are the places where the gravitational pull from two objects is the same. There's a little bit more to it than that, because everything in space is moving, so there's other Lagrange points that also take into account centripetal force and centrifugal force. But anyways, if you can do this calculation, you will have calculated one of the Lagrange points between the Earth and the Moon. Anyways, if you guys have any questions, you guys know how to get hold of me.